Everybody's fascinated with giant stars because, well, they're big, and big things are cool, right? Well, today we want to talk about, well, giant stars. So let's talk about giant stars. If you look at the cool background image I have here, here would be the sun, and Jupiter would be like 1 pixel in size, just unbelievably small, that dot maybe. And we can move up to the star Sirius, and the star Pollux, and the star Arcturus. Wow! Look how big this thing is. But you know what? Arcturus isn't as big as they can get. Let's look at the next image. Oh my gosh! If you can get the idea, the sun would be 1 pixel. That's too big. Sirius, Pollux, Arcturus. This was the picture we just looked at. Rigel, Aldebaran, Betelgeuse, red giant, super red giant, and Taurus. Oh my word. Stars can be very different in size. This is their volume, not necessarily their mass. They're not always the same, but I think it's just cool to see the size. Again, go backward. Look at this. There's the sun, Sirius, Pollux, Arcturus. And here we go here, and my word, they get big. Stars can be very different in size, okay, or different suns. All right, now what we're talking about today is about when you happen to leave the main sequence. All right, what does that mean? Okay, remember, stars are burning. The core of each star burns, okay? So when a main sequence star exhausts its fuel, all right, that's the stuff in the core drops its pressure. So that means the pressure outward. So if we're in the center of a star, it has a particular pressure. But if all of a sudden there's no fuel, it's going to drop its pressure. Therefore, it's compressed by gravity and it will heat up. So again, it gets recompressed and gets heated up. And then as it heats up, this is like a stage in its lifetime, it will increase in temperature. And eventually it will ignite the hydrogen gas outside of the core in a region called the shell source. All right. So notice this is the star, and now it's going to ignite, and we're actually, interesting, it's going to collapse. This is going to be an odd thing. It's going to collapse and then expand, because now, since it's now burning at a warmer temperature, there'll be a greater external pressure in sort of round 2 here, and it will make the star larger. Now, it's not getting more heavy, no more massive, it's just getting larger in volume. Now, the net effect of that, so the shell source increases the pressure out around the core and pushes the surrounding gases outward. The star then expands, which I just alluded to a minute ago. It's going to get bigger into a red giant. Now, the size of the red giant depends on the initial mass of the star. So you can kind of look at the schematic. This is important. You should have copied this down already in your notes. But if not, yeah, copy it, or you could print it too. The rising heat in the contracting core creates a pressure that causes the outer layer to expand. The shell of hydrogen ignites, and boom, it ignites the outside part of it here. Okay, and then the outer layers expand yet more and cool. Now, it may be odd. The core is hotter. But since the same gas is now in a larger space, the gases out here will be cooler. So a red giant is actually cooler than our sun. At least on the surface it's cooler, but on the inside it's warmer. Kind of a weird thing, isn't it? All right. So most of the giant star's volume is in its huge outer envelope, okay, while most of its mass is in the core. Now that's actually an important thing to note. Where this is where its volume is, but if you were going to weigh it, 90%, I don't know the number, but let's say 90% of its weight is right there in the core, producing that energy. Convection carries energy throughout the opaque envelope of the surface. You don't see outer opaque. That's like crazy. It brings it to the surface, okay? Carries energy to the surface. All right, extra words there. As the giant compresses its core, higher temperatures are achieved. And so the temperature inside of a giant, remember in our sun, I want to say it's 13 or 14 million Kelvin, which is quite hot. This is 100 million Kelvin, so much, much, much warmer. All right. Okay, so really quick podcast. We just want to know what happens with giant stars. This is the process by which they go through stages. Probably the key things to understand about the giant stars is that the core has most of the mass, and its temperature is obscenely high, but interestingly enough, the outside temperature is lower, because it's expanded so much and become a giant.